Thanks for joining us for today's webinar. I wanted to start by first introducing myself. My name is Nate McBee. I'm a product manager here at AGI and have been with AGI now for about 14 years. Joined directly after graduate school. I studied aerospace engineering and have spent an extensive amount of time supporting AGI's customers on the systems engineering side of things, from aircraft and UAS systems to those missions a little further away on the satellite and space systems side of things. I'm also part of the OneSky team here at AGI, where the focus is bringing AGI's tools and solutions to the commercial UAS market. This includes capabilities that we're going to see today, of course, with our desktop modeling and simulation tools, but that also extends to activities within areas like unmanned traffic management. We offer analytical web services and lots more that aren't really in the scope of today's webinar, but are all ways we deliver and focus AGI technologies towards solving the problems and answering the needs of commercial UAS industry. So yeah, let's jump right in. So we will focus today on the ability to model beyond visual line of sight operations and analyze the various systems that are involved in those operations. We're going to look at the motivation behind BVLOS operations and how they are requested and perhaps limited today, and point out some of the advantages of being able to provide predictive modeling and simulation of those missions and all of the associated systems. We'll show some of the software tools we use, namely AGI Systems Toolkit software, and how the model-based system of systems approach is used to gain high-fidelity understanding of the pieces and procedures involved in the modeled missions. And finally, we'll tie it together with the ability to use this analysis to help support and supplement waivers and build the safety cases needed for what is hopefully an approval for the modeled operation. So let's just take a look at what Part 107 looks like today, or operations with a commercial licensed UAS operator. I think we're all pretty familiar with what those rules and restrictions are today, but we want to recognize that line of sight is really a limiting factor, I think, to most all operators who are looking to maximize the utility and the effectiveness of their platforms and their various payloads. It's important to recognize, though, that the FAA does have a process for requesting an operational waiver from these rules. Obviously, today we're going to be focusing on the BVLOS portion of that. So, getting a waiver to fly beyond a pilot in command's visual line of sight. And just keep in mind that currently this is an expected minimum of 90 days from submission of a request to finding out from the FAA if it is approved or denied. And currently, currently as of March of this past year, beyond visual line of sight was the third highest requested waiver submitted to the FAA. But it also has a 99% denial rate, right? So these are extremely difficult to get and really require, I think, from the FAA's perspective, a very well prepared and well-designed safety case around those operations. So let's think of the challenges introduced when you consider an operation that is going to leave the visual custody of the pilot in command, right? Once you cross that line from visual to beyond visual line of sight, there are a lot of safety considerations and dependencies on various systems that are involved, right? So you really need to have a high level of assurance that all these systems are really going to be up to the task, right? From beginning to the end of the operation, you really understand all the pieces that are involved and the considerations have been taken and contingencies worked out and everything else to support that operation and that plan. And AGI's history is really providing modeling and simulation tools to the aerospace industry. The typical workflow for use of most any of our tools is to model, analyze, and convey. All right, so modeling the systems that are involved and analyzing their relationships with each other, and the capabilities that you've modeled, and then conveying those results. So, charts and graphs and, just visual representations of those systems. And really, with 30 plus years of building this really massive and robust, spatially aware engine of analytics, really what we're providing is the ability to move objects, attach payloads and systems, look at the interactions of the assets that you have modeled, analyze and introduce constraints, and really visualize that concept of operations, and of course share the results out. So when you think about that typical workflow of modeling and simulation of systems, you really need to start with a properly defined environment of operations, right? So imagery layers and map layers and geospatial information that you may need to bring in, high resolution terrain, wind models and environment models for RF propagation, and really setting up the theater of operations. And then move to mission and system definition. So that could include characteristics of the vehicle itself. Those are performance-based characteristics, how an aircraft perhaps is going to pitch and roll and bank, the route you're going to ask that aircraft to fly, any attached payloads, imagery sensors, communications equipment, GPS receivers, and really analyzing the functionality and relationships between everything that you've modeled. So, that could be simple geospatial situations like airspace and no-fly zones, or it could be a little more advanced, proximity to terrain and proximity to obstacles. You could start looking at system-level performance for communications equipment and GPS for navigation accuracy. And there's really it's kind of a growing list of analysis that can really be supported there. And this is really what STK was built to do, right? It extends beyond the UAS market, obviously, and there's a long heritage there of modeling various aerospace and even defense systems. But the heritage of analyzing just simply moving objects and sophisticated aerospace systems, it makes it a great tool for modeling a conceptual operation and understanding the various mission-critical limitations, and potentially even exploiting design weaknesses. So this is really a great tool to really model, simulate, and understand a mission from end to end. So you can take some of these analytical capabilities and really group them together, or kind of bucket them into some larger groups like communications, navigation, surveillance, and even potentially just include airspace analysis there. These are necessary areas to understand and predict system performance. Answering questions like, can I communicate? And if so, how well? What's the link budget look like? And where? Are there areas where I should avoid due to system level performances that are somewhat degraded? Radar visibility and airspace restrictions and navigation quality and sort of overall health of GPS. Those are things that really go to kind of bolster and solidify a safety case and really an understanding of your expected performances. So let's consider just modeling the conceptual operation, right? Things to consider and things that you're going to want to be able to model. Right? It's very convenient from the STK side in that we can model a lot of these systems kind of all in one tool, right? So we'll take a look at some of these in a little bit more detail and kind of explore how the software can be used to model and simulate some of these various systems. So we'll just start with kind of the first step is understanding the airspace, right? Before you start creating a route or defining locations, it's important to understand where are controlled airspaces, and if you're a Part 107 pilot, of course you're going to be interested in what are the LANT restrictions and where could you potentially gain automated authorization for operations. Airports and national parks and restricted no-fly zones and special activity airspaces. These are all data layers that really enhance the understanding of the operation. You can, of course, bring those in and utilize those. And moving on to just flight planning. bringing in things like geospatial information that you might be using to create your flight plan, very advanced vehicle performance capabilities, modeling the flight characteristics of the platform itself. You can import waypoints or a flight route from other tools, or you can define them within STK. It's a very nice 3D editing capability that lets you point and click out waypoints and flight procedures and things like that. Even taking advantage analytically of the underlying terrain to perform things like terrain following along a route. These are all things that exist, kind of out of the box with STK. And supporting beyond visual line of sight, obviously you have the option for placement of visual observers, and using kind of an STK approach. Placing visual observers and really understanding what their field of view is or their field of regard, understanding terrain considerations and modeling things like the visibility range limits you can expect from a visual observer. And understanding the coverage or the custody throughout the mission at various altitudes, right? What each visual observer can see, assuming 50 feet in altitude versus 200 or 400 feet above ground level. Those are going to look a little bit different. So understanding the coverage at various altitudes is something that you can extract directly out of the tool. And expanding to modeling and simulation of communications equipment, right? Modeling accurately the RF environment and the equipment that's going to be involved. Transmitters and receivers and various telemetry modems and video transmitters, and understanding that these are dynamic platforms, right? They're attached to an aircraft that's banking and pitching and rolling. What type of antennas are you going to use, and the polarizations, and what are the terrain impacts? Even looking at various environmental models that you might want to use from a propagation standpoint. So how are the signals propagated through that environment? Looking at entire link budget analysis between a transmitter and a receiver, or even looking at an entire area and looking at the coverage that you can expect at any point throughout that region or that volume. These are all things that we can explore. You may even consider some more advanced communication systems, such as modeling cellular communications or SATCOM relay systems. Understanding urban terrain effects, bringing in building shapefile information and using that for signal propagation and refraction. These are all really advanced capabilities that exist that you can take advantage of to gain a deeper understanding of some of those more advanced systems. And we've mentioned GPS and navigation previously. STK and AGI's heritage really is started with satellites. So we can really accurately model and predict positions for any of the GNSS constellation that you might be using. So GPS and GLONASS and IRNSS and whatever else you may be considering. Bringing in highly accurate predicted orbital information for those satellite systems and being able to look at things like what would be the expected number of satellites available to your aircraft. And based on the position of those satellites in the sky at that given time, what is the quality of your navigation solution in terms of like dilution of precision, so horizontal dilution of precision or overall positional dilution of precision. Those are things that we can explore and look at, and that obviously helps you to understand what the implications might be for operating in a certain geographic region at a specific time, given the dependency of a GPS type of constellation. And understanding visibility from surveillance systems. So you may be operating on a range, or maybe it's somewhere and you're interested in predicting whether or not the aircraft itself is going to be visible by a known radar location. So we can model very broad area radar systems and look at things like what are the probability of detection and signal to noise ratio given the local terrain, and maybe you're interested in 400 feet above ground level, and you want to model local clutter, and we can really start to get deep into the details of modeling these types of radar analysis. But just understanding, simply, would you have the ability to be seen and tracked by a known radar location? So think about all of the things that kind of we've highlighted up until this point, and try to make the connection of how to use that type of analysis to build your safety case, right? Demonstrate a deep understanding of your equipment and the limitations, the ability to adjust operation plans accordingly, given new information about those systems, and different design considerations. And using that understanding and that knowledge to to potentially supplement a waiver request with the demonstration of that level of understanding, and even considering things like crew coordination and safety training strategies that you plan to outline that you're going to employ along with your FAA waiver request. Using a tool like STK really isn't just for modeling and simulation and understanding of these systems at an engineering level, but it can really be used to, almost as a briefing tool, a mission briefing tool, end to end, the entire modeled system and simulation of the operation, getting everybody on the same page in terms of the crew and the people that are supporting this particular mission. Understanding the contingencies and understanding their roles and their responsibilities and expectations of how the mission's going to play out. So this can really be used as sort of a final briefing tool as well. So anyway, let's dive into the software itself. I just wanted to open that up and show a couple of things, get some experience and show how the tool itself looks and how it's used, and kind of the analysis and the results that you can kind of pull out of that. So let's go ahead and open up the tool itself. All right. So what you're seeing here is just the STK software, the GUI, and this is where we manage and maintain all of our specific objects, whether we're modeling aircraft or radar systems and communications and running analysis. So, we'll walk through some of this as a demonstration. And you can see a lot of data layers and information here in the 3D window. So, I can go in and manage a lot of different data sets and sort of toggle them on and off as needed. And of course, this is just like I've mentioned before, just a three-dimensional globe window. And all of our terrain data and information and those sort of things are added into our system. Right? So I guess we'll first look at kind of the workflow of how we were modeling some of those features and points that we defined in some of the previous slides. So here you can see just sort of an area of operations that's being defined. So this is a relatively large area, and our goal here is to put the appropriate visual observers in place and model our flight plans and analyze some of our systems. So this is just a real quick sort of modeling overview of what's involved in that. Bringing in that information, this could be a shapefile or KML or something I've imported into the software, or something I've manually created. And we'll take a look at modeling the actual flight plan itself. So just turn that on here. And as mentioned previously, of course, this could be imported from another tool, or if you wanted to, you can of course use the STK GUI to sort of click that route out, right? And you'll notice the terrain following capabilities if we zoom in and look sort of side profile here. So it's using some of that terrain information to go from point A to point B and sort of terrain follow. So if we actually look at editing this, you'll notice that this is really just a small collection of waypoints that makes this route definition, right? So it's relatively simple for this. And if we were to then, of course, put in our pilot in command or our GCS location and things like that, I've designated a specific location for my pilot in command, right? So you can see that there. And then, of course, all the other visual observers. So if I look through this list of objects that I've modeled, I'm just going to turn on some of these particular visual observers. So added just a handful of those to cover the representative area. And each one of these is sort of supplied with its own visual limitation. And I can visualize that in the software by showing some of these dome looking sensors, right? These are meant to be kind of a visual representation of what their visual capabilities would be at determining and maintaining visual custody of the aircraft while it's within their particular area. And once I have those placed, I can start to look at things like, what does coverage look like given the placement of these visual observers? And this is at 50 feet above ground, right? So in the first 50 feet of my mission, if I'm trying to spin up to altitude or whatever my procedures are, I want to make sure that I'm within line of sight of my pilot in command. But as I transition, above 50 feet, maybe up to 200 feet above ground, do I have any gaps in coverage, and who's going to be able to see that particular aircraft, and do I have any gaps or holes to fill there? Right. So this is a great way of understanding what those visual limitations are. Right. And it's also, just to point out, this is a dynamic platform, obviously. So if I wanted to simulate this this flight plan or this mission, I can of course just use some of the animation controls and really understand that and change my perspective if I wanted to, zooming and changing things to look at perhaps my particular flight plan and my aircraft that's involved. So looking at this particular aircraft, and I'm going to slow the animation down quite a bit here just so you can see there's a lot of things to consider when an aircraft is flying through these flight plans. It's pitching and rolling and banking and doing things that are a little bit more realistic for that particular airframe because that's the way I've defined the airframe itself within the software. Right. So we've looked at visual observers and modeling flight routes and those sort of things, looked at the aircraft itself. Now, one of the things we mentioned previously was the communication system. So actually, let me turn those back on and zoom back to this aircraft. You'll notice that some of these communication systems that are modeled are attached at various locations on the aircraft, just to represent maybe where they would likely be placed or where they are placed for my particular airframe. And I've modeled a couple of different ones here, like you'll see in the list a long-range receiver and a telemetry radio. I have a specific transmitter for my video. So I'm really trying to model some of these notional systems, and these are all done via a GUI definition interface as well. So if I know my video is relying on a certain frequency and a specific power, I can go in and define those. Look at the antenna that I'm using, or choose from a list of a lot of different antenna types, and maybe even bring in my own antenna pattern file and associate with it. So I can get really detailed with modeling some of these systems. Polarization of my systems, different modulation schemes. If I have very specific types of digital modulation for my communication systems, I can of course point to those. And if I've employed any sort of filtering methods, I can of course introduce that as well. So what you're seeing in the 3D window really is the resulting gain pattern from a couple of different antennas, right? And these are kind of a very simple dipole type of antenna. And even looking, if I were to zoom out again here, I know that my pilot in command location and model various systems that are involved there. So, if I were to look at let's say the video transmitter or the telemetry radio, if I turn that on, you'll notice this green line going between my GCS and my aircraft, right? And this really signifies, let me animate through, this really signifies that there is a valid communication link between the GCS and the aircraft, right? And we're visualizing that with this line. On the STK side, we call that access, right? So that's telling me that I actually have access to communicate between the GCS and the aircraft, and I can see that there, right? So that's my my communication link. And how good is that particular link? Well, STK can obviously run report and graph information based on that access. So, for example, if I wanted to look at my control link, right, I can see this is received power for my RC control. So I'm looking at things that are changing along the vehicle route in this graph. Or I could look at that from a sort of a regional coverage as well. Right? So my RC link at 200 feet, right? What does that look like? And you'll notice some areas, and again, this is just a received power scale on the coloring here. One of the interesting things to note here is that we do see right above the pilot and command sort of a null and a low power spot there. And if I were to change my point of view and zoom to my pilot and command, zoom directly in, right? I'm right above where that is. And assuming a dipole antenna was modeled, this is kind of what you would expect, right? That you do have null and low power, and that's directly above where that dipole antenna is. Right? You can sort of see that that characteristic dipole pattern there, right? And that's at 200 feet. So if we were to change this to say 400 feet, right? You do see some differences between those, right? There's going to be some slight differences from various altitudes. So really being able to dig in and understand what those differences are. Right? And another thing that we can model and might want to take a look at is just and understand is from the antenna perspective, right? This video transmitter has been defined with a really specific type of antenna. This is like a multi-turn helix antenna, and it's actually being simulated from a sort of an antenna tracking perspective. So as the aircraft moves through its flight route, if we animate, you'll notice that antenna is sort of gimbaling and turning and kind of tracking that, right? So we're simulating that behavior in the antenna itself, right? So this lets us understand kind of a high gain, very highly directional antenna being steered and pointed at the aircraft, and understand what that system is, how that system's going to perform. Right? Another thing to consider in a lot of these situations is kind of interference types of signals, right? So as a quick demonstration of that, I've modeled a couple of cellular towers here. So let me turn those on, and sorry, the screen's getting a little crowded here. So I'm going to turn off just the visual labels of these visual observers just to clean up the screen a little bit. But here you'll see a couple of cell towers that have been placed and modeled, and each one of these cellular towers is modeled with a representative cellular transmitter system. So if I get my viewpoint right here, you can sort of see those antenna patterns on those towers. Now the reason for modeling those towers isn't because I plan to use cellular for my command and control link or anything like that. But I can use those emitters because the cell phone towers are emitting signal strength. I can use those in a full communication system type of way where as I turn that modeled communication system on, these yellow links signify potential interference sources to my receiver on board my aircraft. And this green link is signifying that's my primary link. So I'm really looking at situations where, based on the locations and the powers and the frequencies of the cell towers, and they don't have to be cellular, they could be any known emitter source. What is that going to do to my signal strength? So this just so happens to be very close in frequency to our telemetry radio. So if we run a report on this, we would see things like, in black here, this is sort of my perfect world carrier to noise ratio, right, without any sort of interference being considered. And in the green, you're seeing that same telemetry link, but with the consideration of the presence of these cellular towers. So what do their transmitting equipment do to the kind of the noise floor, and am I going to have any crossover and sort of bleed into my bandwidth, and kind of what does that look like, and what does that do to my signal? Right, so I can start to really understand what what the limitations would be in the presence of those other known emitting sources. And an interesting thing to look at on our antenna tracker, this is one thing that I noticed while looking at this. Let's see. If I were to look at, let me figure out where that was again. This is my FPV video receiver that I've modeled here. If I were to go into the reporting and graphing manager for this, and I look at the link, or what we call the access link between my FPV video receiver and my transmitter on my aircraft, if I were to look at something like received power and run this graph, I'm looking at particular situations throughout the flight route where what's my signal strength or my received power look like. And there's some interesting dips in this curve, right, where I may experience some pretty rough video. I'm used to seeing really nice clear video, and then all of a sudden it starts to get jumbled and sort of muffled up. So just looking at that particular time in my animation, I can jump directly to this point in my route where the signal strength is about to sort of tank on me. And if I were to zoom in, let me focus on my aircraft. I can zoom in and I can start to see what this aircraft is going to do. I'm going to turn my comm system off just so we focus on this link. I can see that I'm approaching a banking in my flight route. Right? So if I were to animate along here, right, and my aircraft right around this area starts to bank and initiate a turn. My FPV antenna, you can see that link directly right here, is really going through a null in my antenna gain pattern. Right? So I can really understand some of the things that I may want to do to mitigate those situations. Limit my bank angles and things like that. So it's kind of interesting to see those specific situations and kind of understand those limitations of the systems. And I don't know if there's anything else in here we really want to dig into. Obviously, we've modeled, you can see in the list, all of these satellites, and we looked at things like the GPS quality. So I can turn that on as kind of a visual layer. So at kind of low to the ground, 50 feet above ground, this is what I would look at for number of satellites. And green if I'm above my my comfort level of number of satellites available to me, and anywhere in yellow or red, is for me as an operator would be kind of a no-go, no-fly sort of situation. And if I look at this entire region over the time span that I'm going to operate, or proposing to operate this mission, it's really just a small area here where I see number of sats. So I'll at least know to stay kind of out of that area. And I can define that a little bit further just by looking at what the the horizontal dilution of precision would be, given all of those satellites available and kind of the quality of the solution that the GPS receiver should be able to resolve to. So we do see a minimal effect over there, but this is a nice way to look at those, the performance of some of those systems. Right? So I don't know if there's really anything else to look at in the software itself. I think we highlighted a bunch of things here and kind of ran through it really fast. Obviously, happy to take any questions or anything that might be on the minds of anyone out there. If you've seen something and you have questions about it, let us know in the chat window. So thank you for your attention and for attending today's webinar. If you are looking for any additional information, you can visit the AGI website, agi.com, or of course the OneSky website, that's onesky.xyz. All right, and thanks again. Bye.